the busiest shipping lane on Earth. Every single day, hundreds of cargo ships, oil tankers, and passenger vessels pass through this narrow stretch of water. Just 22 miles wide, yet for centuries it stood as one of the greatest natural barriers in human history.
The English Channel. Cold, unforgiving, constantly moving, separating Great Britain from mainland Europe. For more than 200 years, engineers, politicians, and dreamers imagined a bold idea. What if this water was no longer a boundary, but a connection?
The idea of a tunnel beneath the English Channel began in 1802. At the time, there were no electric lights, no modern engines, no computers. Transportation relied on horses, sails, and oil lamps.
By the 1880s, test tunnels were started on both sides of the channel. And that's when reality struck. Water flooded the tunnels. Pressure overwhelmed early machinery.
After 4 failed efforts, Britain and France finally reached a historic agreement. This time, the goal was not just a tunnel. It was a permanent economic and transportation link between 2 nations. 2 countries, one shared risk. Engineers knew one tunnel would not be enough. The final design included 3 parallel tunnels, 2 rail tunnels, and 1 service tunnel. On the French coast, the village of Sangatte became ground zero. In England, excavation began beneath the iconic white cliffs of Dover. The route passed through chalk marl, strong, stable, and mostly watertight. Too high and porous rock could flood instantly. Too low and sticky clay could crush machinery. The target zone was only 20 meters thick, buried 75 meters below the sea. France dug a massive 60-meter shaft, creating a launch point for the tunnel machines. Britain had to blast 250,000 cubic meters of chalk to create a flat entrance on the cliffs. 11 tunnel boring machines were custom-built. Cutter heads weighed 600 tons. Robotic arms installed watertight concrete segments behind them. Inside the machines, temperatures soared above 120 degrees Fahrenheit. Underground work at the limits of human endurance.
We have a pressure spike in the lower quadrant.
I'm on it. Increasing torque now.
Levels stabilizing. Good adjustment.
The service tunnel advanced first, every meter a test. Water seepage had to be sealed immediately. A breach could trap entire crews. Once underground, there were no landmarks. Engineers relied on gyroscopes, electronic compasses capable of detecting even the smallest change in direction. After removing 7.5 million cubic meters of rock, Britain dumped spoil into the sea, forming a new 90-acre coastal platform. They didn't just dig a tunnel, they created new land. December 1, 1990. A small pilot hole broke through. 2 sides had met. The final alignment error was less than half a meter.
We finally broke through!
The main rail tunnels followed, built for high-speed trains traveling up to 100 miles per hour underwater. Ventilation became critical. Giant fans cycle fresh air every few minutes. A ventilation failure would be catastrophic. Fire was the greatest fear. Every 375 meters, escape routes connect to the service tunnel, the lifeline. While engineering succeeded, finances spiraled.
Initial cost estimates, $4.7 billion. Final cost, $9.55 billion. Terminals at Folkestone and Coquelles were built, massive logistics hubs. Cars, trucks, and passengers roll onto rail shuttles. 40 minutes later, they emerge in another country. Years later, the worst-case scenario occurred, a fire inside a truck shuttle. The safety systems activated. Every life was saved.
Stay close to me.
Don't look back, we're almost there.
With high-speed rail upgrades, travel time from London to Paris dropped to just over 2 hours, faster than flying. No airport delays.
The Channel Tunnel stands as one of the greatest collaborative engineering achievements. They once said the sea was an unbreakable wall. This tunnel proved human ingenuity can overcome nature.
This is not just a tunnel, it is a statement. And the next impossible challenge is already underway. Subscribe for more stories of engineering that changed the world.